Okay, so today I'm going to be talking about the Astro 3D Centre of Excellence. In the first few slides, I'll give an introduction into how Astro 3D came to be proposed, and then I'll give an introduction into what we're doing in Astro 3D, including our science goals and the telescopes and instruments that we're using to achieve these science goals. It's quite a broad-ranging centre, and we also have large national education outreach programs. We have tech transfer and IP development within the centre, and we also have diversity, really ambitious diversity targets, and we also do diversity research as well. So first up, let's see if I can advance here. Yeah. Okay, so first up, our Centre of Excellence, it's a $40 million Australian Research Council centre, and some of the chief investigators and partner investigators are listed here, but we've got around 250 members of the centre altogether. And we have 3 science goals in the centre. The first goal is what are the sources of reionization, how were they distributed, and how did they evolve across cosmic time? How did the mass and angular momentum build up in galaxies across the universe? And then how did the chemical elements build up in the first stars and then the first galaxies? And how did they evolve in galaxies across time? So how did Astro 3D come about? Well, the Australian Research Council offers these centres of excellence every 3 years. You can apply for them. They typically have about 20 centres of excellence at any one time, and these across all areas, including things like arts and the humanities and various areas of science as well. And so when I moved back to Australia in 2011, I was involved in the writing of the Australian Decadal Plan for Astronomy from 2016 to 2025. And this was just a really great thing to do after moving back to Australia. Because I'd been in the US for 10 years, I hadn't been really aware of some of the major changes that had happened in Australia while I was away. And so this was an excellent chance to get up to date with those changes and then really have a think about the big picture and what major problems we can solve in Australia with Australian facilities access, as well as personnel that are in Australia. And while writing this plan and doing the statistics for the plan, it became apparent that there'd been a real major change in the demographics in Australian astronomy over the previous 10 years. So for example, in 2005, which is about when I left Australia, we had quite a lot of optical and infrared astronomers, 51%. And then most of the rest of the community were radio astronomers, about 30%. And we had a fairly small fraction of our community, 12% were theorists. After I moved back, what had happened was that the number of theorists in Australia had increased dramatically, and we now had 32% of our astronomers classified themselves as theorists, 20% radio astronomers, and then 40% optical IR astronomers. There are a couple of reasons for this. One was that Australian universities had been hiring a lot of theorists over those few years, from either theorists who were based overseas, and some of them were Australian, others were not Australian. But basically the theory component of Australian astronomy increased because during that period we also had very limited access to large telescopes. So access to 8 to 10 metre telescopes for a period of time was almost non-existent. The government did provide some funding for us to buy time on Keck and also buy time on Magellan. And at some point Subaru, but this was a fairly small amount and it really wasn't enough to serve the optical infrared community. And so what happened was some departments then decided it was a better option to hire a theorist. This was an excellent thing to do, because what it meant was that we actually could then think about big problems where obviously you need to combine optical, radio and theory together. So in the decadal plan, we thought about what's on the horizon for Australia, and Australia is a partner in the Giant Magellan Telescope, and along with you all there at Harvard, and the Square Kilometre Array is also going to be built in Australia. Well, half of it is, and this is the high frequency end, which is key for the studies of the Epoch of Reionization. And fortunately, at around the same time scale as the Australian government, we were able to convince them to join ESO as a strategic partner, which means that we had suddenly access to a wide range of instruments on any of the VLT telescopes. And so at that time, we really felt a bit like kids in a candy store. And these actually are my kids in a candy store. And it really was very much like that. So we could really think big picture, think about what sort of problems we wanted to solve, especially given the ESO large programs that we could propose for. So I proposed for a $40 million Centre of Excellence, and we combined Australia's major astronomical institutions. So we have 6 universities in Australia, along with CSIRO, and NCI is our national supercomputing facility. And then we selected international partners based on existing collaborations, but also collaborations that would provide basically complementary expertise, complementary access to telescopes, and access to additional supercomputing facilities. And in particular, I want to highlight the Chinese Academy of Sciences, because they're running the FAST radio telescope, which is the largest single dish radio telescope in the world, and they're conducting a complementary H1 survey to our Australian H1 surveys using the Square Kilometre Array Pathfinder. So the Astro 3D Centre of Excellence covers a full range in redshift from the Epoch of Reionization right up to the present day, and including studies of our Milky Way. And so each of these, I'm going to run through some of our surveys and projects, and these surveys and projects basically connect together in redshift. And then we have a big theory program which combines or links together the observational programs. Where possible, we're doing radio and optical studies, and this is really to get at the hot gas as well as the cold gas. Okay, so the first goal of the centre is to really detect the sources of the Epoch of Reionization, and then to track those sources across cosmic time, so the stars and the formation of the first stars and first galaxies. And so these are simulations. These are 2D simulations of what we might expect to see at the Epoch of Reionization with the Square Kilometre Array Telescope. What we're aiming right now to do with the Murchison Widefield Array, which is in Western Australia, is to detect the Epoch of Reionization. And we're currently doing simulations for the Square Kilometre Array to predict what we think the Epoch of Reionization might look like. And here's an example in 3D, which gives a much better picture of what we think the Epoch of Reionization would be like. You can see that the red is the neutral hydrogen, and the white are the first stars, and they're ionizing the gas. And you can see that we go from an opaque universe to a transparent universe over time. But it did look kind of, Swiss cheese-like for a while. And so what we really want to do with the SKA is map this in 3D, rather like the simulation here. And this simulation is produced by our theorists at the University of Melbourne, and that effort's led by Stu Wyeth. Okay, so once we have an understanding of the Epoch of Reionization, we actually would like to understand how those sources evolve across time, and also how the fraction of ionizing sources changes with time. So in the modern day universe, we have, in galaxies, we have different sources of ionization. We've got stars and we've got AGN, and then we've also got shocks produce ionization from supernova galactic scale winds and also AGN processes. And these presumably evolved across time. There's very little understanding of how that happened. So we're combining a range of different telescopes to cover the full redshift range. We're using the SkyMapper telescope, which is in Coonabarabran in Australia, to discover the older stars, and I'll show you later in my talk a couple of key discoveries with that. We're aiming to use this James Webb Space Telescope when it goes up to look at the first galaxies, and in particular we're interested in understanding the chemical abundances of those. And then we're tracking ionizing sources across cosmic time using the VLT and Keck, as well as the Anglo Australian Telescope for nearby galaxies. The second goal of the centre is to understand how galaxies formed and evolved, and we're again covering the full redshift range from the first galaxies right up to the present day. And we're doing that in the high redshift universe using gravitational lensing. The aim of this is to, at the moment, look at galaxies out to redshift of 4.5 using the VLT and Keck, but also in future, we're aiming to use the GMT to do that, to push this out to higher redshift. And then, of course, using James Webb when it goes up as well. In the nearby universe, we can do this quite well, actually, with the Square Kilometre Array Pathfinder telescope, which gets data cubes in H1, and also the SAMI HECTOR survey on the Anglo Australian Telescope, which is getting optical data cubes. And that the first survey is complete, and I'll talk about that as well. Now, we're called Astro 3D, and sometimes I get questioned why 3D. So we're tracking, angular momentum and the buildup of elements and mass in galaxies. So we really need the spatial information. We need spectra at every pixel in order to measure the elements. So this is a typical optical spectrum. And so we have sulfur lines. We've got nitrogen, hydrogen, oxygen, hydrogen, and another oxygen line down here. And these are what we use to measure the ionizing sources in the galaxies, as well as the chemical abundances. And we can use these to actually measure the fraction of ionizing sources and how that changes across the galaxy and how it actually changes per emission line as well. And then also measure the chemical abundances. So it's quite a powerful technique, and our aim is to get, in time, to develop tens of thousands of data cubes of galaxies in order to do this in a statistical way. A third goal of the centre, using those same observations that I mentioned to you, is to try to understand the origin of the chemical elements. And again, we start off at the highest redshifts, and we're also looking for the older stars using galactic archaeology in the Milky Way. And then we plan on using James Webb. We're currently using Hubble to find our targets and then these are gravitationally lensed galaxies. And then we're tracking them across cosmic time and using those same observations, VLT, Keck, and the SAMI instrument on the Anglo Australian Telescope. Now, we are discovering the first stars, as I said, using the SkyMapper telescope. And SkyMapper takes images of the sky every night. So every night there's an image of the full southern sky. And then we find candidates of those first stars, and then they're followed up on the VLT. And so far we've discovered the 3 most pristine stars in the universe. And so very exciting results from that survey. And in particular, this is part of our Galactic Archaeology program, which is a large program to study the chemical elements and the build-up, basically the chemical and the accretion history of the Milky Way. This survey is aiming to obtain spectra of 1 million stars in the Milky Way, and we currently have high-resolution spectra of 500,000 stars in the Milky Way. So the history of the Milky Way is built up in this survey through chemical tagging. So we measure the chemical abundances and the ages of the stars, and then theoretical models predict that if we have 1 million stars in the Milky Way, then we will be able to track back the history of the Milky Way. In our centre, we've got a radio optical as well as theory for all of our surveys and projects. And traditionally in Australia, the optical community and the radio community haven't been really collaborating very much together. They really were operating separately and rather in silos. And as I mentioned earlier, we really didn't have a big theoretical community until more recently. And so there hadn't been built up major collaborations between the theorists and optical astronomers or radio astronomers. And so this is one of the major advantages of having a centre of excellence, is that we have the funding and the long-term funding. It's a 7-year centre in order to do this. And so we're really trying to track the cold gas, the hot gas, and the stars, and then combine them with the theoretical simulations for galaxy formation evolution. And so our theoretical simulations are called the Genesis simulations. And what we're doing is we're combining cosmological hydro simulations with semi-analytic models. in order to probe different spatial scales. So to create mock data cubes for our surveys, and specifically for our surveys, so covering the same mass range, and actually running the model data through our instrument response functions so that we can actually produce directly comparable data sets to our surveys. And so we're combining the zoom-in simulations from the Cosmo hydro simulations with semi-analytic models where needed. So now I'm just going to run through some of the science highlights and discoveries of the centre. And so this is one that I really like for the Murchison Widefield Array experiment to try to detect the epoch of reionization. This is really like trying to find a needle in a massive, massive haystack, because we have so much noise in front of the epoch of reionization, including foreground noise from our galaxy. And so our astronomers from MWA have come up with the technique to remove the brightness of the Milky Way by measuring that from the reflections on the moon. At the Epoch of Reionization team now actually has about 7 years worth of data, and they're going to need another few years worth of data in order to detect the Epoch of Reionization. But we have managed to improve our ability to detect those limits by a factor of 10. So we've actually reduced the limits by a factor of 10. And this is led by Nicole Barry, who's an Astro 3D postdoc at University of Melbourne. First Stars team discovered, as I said, the 3 most pristine stars in the universe, and particularly this one's particularly exciting. It's the most iron poor star known, and this was led by ANU Astro 3D postdoc Thomas Nordlander. Chen Yuan, who she was a PhD student at University of Hawaii with me, and she's now an Astro 3D fellow at the at Swinburne University. And she discovered the most distant spiral galaxy. So she had developed a sample of spiral galaxy candidates using lensed galaxies. And she's trying to understand how spiral galaxies form, in particular their structure. And she discovered a galaxy with a clear spiral arm. You can see it right here. It has, clearly marked spirals. And this is beyond redshift of 2, which provides tension with the cosmological hydrodynamic simulations, which tend to form spiral arms later in the universe mostly. A really exciting result very recently in our centre is that we have an Astro 3D Fellows program. It's similar to the Hubble Fellows program, where people can apply for the program to take the fellowship at different universities in Australia. It's a 4-year fellowship rather than a 3-year fellowship, and fellows can also choose, if they want to take their fellowships overseas at our international partner institutions, or they can take it across different universities in Australia as well. So it could be 2 years at one university, 2 years at another, for example. And so we have fellows in different areas. They're covering the full range of surveys and projects in our centre. And for example, Caroline Foster here is doing research in the SAMI Nearby Galaxy Survey. This is the one with the IFU data cubes. Trevor Mendel looks at high redshift elliptical galaxies. Claudia Lagos is a theorist, and she develops semi-analytic models for galaxies. Elizabeth de Cunha does a combination of radio and optical and infrared studies of galaxies, and in particular she's developed theoretical models which can be used to measure stellar masses and SEDs of galaxies. Emily Wisniewski does high redshift star-forming galaxies, and Chen also high redshift star-forming galaxies. And so you can see there's a range of expertise in our Astro 3D Fellows, and they got together and decided to apply for a very large VLT time, very large proposal, and they were awarded 200 hours, which actually is the largest amount of ESO-Muse time ever awarded. And they're aiming to look back what they call the cosmic Middle Ages, and this is at around redshift of 0.5 in order to understand the build-up of galaxy angular momentums at those redshifts. Now our SAMI survey is complete, and this is the survey of 300 data cubes in the optical of galaxies. And this survey's prime goal is to understand the angular momentum and how that builds up in galaxies. And they found that galaxies rotate and the angular momentum is closely related to large-scale structure. And this is a survey that's been led by Julia Bryant and Scott Croom at University of Sydney. But there are investigators across all of our centre involved in this survey. The GALAH survey of the Milky Way achieved its halfway mark of 500,000 stars. They're actually just about to release the whole 500 star catalogue. So if you're interested in that, it's due out in December. And that team have made some really interesting discoveries for the Milky Way, and that includes this discovery you might have read about, a massive flare that was produced by a supermassive black hole in the past, is 3.5 million years ago. And they used a combination of studies to determine this, including X-ray and H1 observations, as well as looking at high ionization lines, so carbon 4 to carbon 2, silicon 4 to silicon 2 along the Magellanic Stream. And the Galactic Archaeology team also has been looking at the chemical abundance of nearby groups of stars and outlying groups outside the Milky Way to try to understand the build-up of our galaxy itself. And they found 2 outlying groups that have the same chemical abundance as stars in our Milky Way. And they think it maybe this was associated with a past interaction or collision, perhaps a collision with a dwarf galaxy. And so I'm just going to now focus on some of my own research within Astro 3D. I still have some time for research myself, and I'm leading a team, and we're continuing to develop our theoretical models for understanding galaxy spectra across cosmic time. And at the moment, we're mostly focused on building our models ready for James Webb and to understand galaxy evolution, in particular chemical abundances and ionization states in galaxies across cosmic time. So here are some examples of what we've been developing, and these are, you can find these in my annual review article in 2019. And these are new chemical abundance diagnostics specifically designed for the UV, and also they actually cover the full range right up to the infrared and also sub-millimeter. So it's a full range of UV, optical, infrared and sub-millimeter diagnostics, and they include metallicity diagnostics as well as ionization parameter, as well as pressure diagnostics for galaxies. And you can see there's some really good diagnostics, particularly there's these aluminium diagnostics. They're not very sensitive. These are ionization parameter diagnostics. They're not very sensitive to metallicity, for example. And you can actually measure now the ionization state of the gas in galaxies as a function of redshift, because we now have self-consistent diagnostics in the UV, optical and infrared. And we're hoping that we'll be able to apply these out to redshift of 6 with James Webb. Now, we're also developing our models to become more realistic models. So at the moment, many photonization models, ours don't, but many photonization models assume a constant temperature or a constant density. And in particular, our models also, they do assume a spherical nebula or a plane parallel nebula. And we know that this just, it doesn't happen in galaxies, obviously, or H2 regions. So you can see here, we measured the electron temperature structure in Orion, and it's clearly not constant with radius. And we also measured the density structure on the right here, and this is definitely not constant, and so we really can't make these assumptions. And this also makes it clear that we need to be able to put in complex density structures in our models rather than the simple density structures. So what we're doing is we're building 3D Monte Carlo simulations, and this is work that's being done in collaboration with Ralph Sutherland and my PhD student Yufei Jin at ANU. And so this is really designed to put our ionizing source inside a arbitrary geometry. We're using log normal densities at the moment, density distributions. And then we're combining our mappings photonization models with new Monte Carlo simulations to actually run each photon through the arbitrary density distribution, and then we sum up the output
We seem to be having technical difficulties.
It's in there and it's extremely detailed. So this is the most detailed chemical element radiative transfer Monte Carlo simulation there is. And we can produce maps. These are H2 region maps. So we've got H alpha here. You can see sulfur 2, nitrogen 2. They look fairly similar to observations of H2 regions with similar spatial resolutions. And on the left-hand side, you can see the fluxes that we get. Now, when we had spherical geometry, which is the x-axis, before now we can compare that with the fractal geometry. So that's with the 3D code. And you can see that the hydrogen lines and the oxygen lines, the O3 here, they're not affected really by having whether you've got a spherical or a fractal geometry, but the lines that are produced further out in the nebula, which are very sensitive to the ionization parameter and how that diffuses, so how it goes down as a function of R squared out in the nebula, are very affected by whether you have a 3D geometry, a 3D model, or a plain 2D spherical model. And so you can see here that in the fractal geometry, you have higher, you're predicting more sulfur 2 and nitrogen 2 than the 2D models. And so this is going to have important implications for how we model galaxy spectra in the future, also for our metallicity and ionization parameter diagnostics that use those lines in particular. Now, one other problem with the models is that we had pretty much an outdated abundance scale. So all of the photoionization models in the world and the stellar evolution models are using these abundance sets, typically Anderson-Grives, and scaling them just straight up with metallicity. And so all the elements were scaling together with the exception of carbon and nitrogen, where we had to import a primary and a secondary element, and it was sort of done really ad hoc. And so what we did, and this is work done by David Nichols, a postdoc at ANU, is to look at modern spectral observations, H2 region observations, as well as observations of blue compact dwarf galaxies, and derive what we call the concordance abundance scale, which is a data-driven abundance scale based on your real observations of how the different elements change relative to each other as a function of metallicity. And on this big plot here on the right shows you clearly why we need to have a new data-driven abundance scale, because the previous one here, Anderson-Grives, the black dash line doesn't fit through the data. So that means that the chlorine to oxygen ratios that we were using were just plain wrong. And this applies to many of the chemical elements, so it actually does make a really important difference. So now I can show you the results of the comparison between the old abundance scale compared to the new abundance scale. And so if you scale the elements uniformly, which was done in the past, you'd get this black curve here where we're comparing Sloan data with the emission line ratios in the optical, oxygen 3H beta and N2 and O2. And this is a good one to compare because N2 and O2 is a metallicity diagnostic, whereas O3 and H beta is primarily sensitive to the ionization parameter. And so in our new concordance, which are in red, we can actually fit the data, whereas before we were unable to fit the data. And this plot on the right shows you 3 different uniform scaling methods which were done, which we were doing before, and none of them actually fit the data. And so this highlights the importance of using data-driven abundance scales. Now we're developing, with these new concordance abundances, we're running, using MESA, new stellar tracks for the massive stars. We've calculated new opacity tables. We're now putting them through new stellar atmosphere models and then running them through our stellar evolution synthesis code, which Ralph Sutherland has developed. So this will provide self-consistent abundances throughout the entire model system, and including into our 2D and 3D photoionization model codes, which we're then going to compare together. The other thing we're doing is we've taken observations of single star H2 regions in the Milky Way, And in addition to helping constrain our concordance abundances, we used these to solve for depletion factors. So we got really high resolution observations, and so these and allowed us to solve for all of the chemical elements as a function of metallicity to constrain those depletion factors. So this is all work that's due to come out in the next year or two. Now, that's work that I was doing, and I want to just return now to Astro 3D. So that's work within and embedded within Astro 3D. Now, Astro 3D is a centre of excellence, and this is publicly funded using taxpayers' money. And so in order to get a centre of excellence, we have to demonstrate significant national benefit, and that's not pure science in the Australian Research Council terms or the Australian government terms. Pure science isn't enough. We have to be able to demonstrate really significant national benefit. So in the centre, we're doing technology transfer, outside astronomy. We have large education outreach programs. We're transferring skills and expertise. These are basically astronomers that we're training to go outside astronomy if they choose to do so. We have diversity initiatives, which I'll talk about, and then we have sustainability initiatives as well. So we're really trying to lead the way in these areas for centres of excellence. So, for example, tech transfer is something that is actually fairly it is done broadly in astronomy, but it's not that well known how often it occurs, and we can probably be doing a better job. So we have a lot of technology developed for the radio telescopes as well as for the optical telescopes, and I'm going to, here's an example. So our SAMI HECTOR telescopes use, fibre bundles, and we've developed these robotic positioners which vibrate these fibre bundles along the focal plane on the telescope so that we don't have to plug fibres anymore. And so there's a lot of new technology coming into these, and also including, we can miniaturize spectrographs. And so here's some examples of the tech transfer that has happened from the radio and optical side. So for example, the fibre optic lab that has developed those fibre bundles also work on transferring those into other areas. So for example, our Chief Investigator, Joss Bland Hawthorne's lab, are now working with Horticulture Australia, and they've actually developed the spectrographs that are used on these these are robots that walk along farms. They walk along the crop rows, and they're solar powered, and they actually use the spectrographs to detect bacteria, so like salmonella, things like that, because you sometimes get these on crops like spinach or broccoli. And so this is an obvious way that astronomy is actually benefiting other areas, in particular in health. Also in health, our Chief Investigator Kath Trott and former astronomer Ilana Fein, they used radio astronomy data processing techniques and applied them to cancer treatment. And so when people are having radiation therapy for cancer, their bodies are moving because they're breathing. And it's similar to some of the processing techniques you need to do for radio astronomy due to movements in the ionosphere, for example. And so they applied similar techniques, and based on the radio astronomy, were able to come up with a method that actually corrects for the movement of the body so that the radiation can target the cancer rather than the surrounding tissue. A really clever technique. And so they received $2.6 million for a startup company, which Ilana is now leading. We have a sustainability committee, and this committee has calculated all of our carbon impacts, our carbon footprints, including air travel or supercomputers, and they're making recommendations to us for how to run conferences and workshops, in-person ones that are carbon neutral, as well as running sustainability seminars and helping us with our merchandise choices in the centre. We have national education outreach programs, including our Telescopes in Schools program, where these are philanthropically funded telescopes, and then we train the teachers, and then we send astronomers out to help the students do projects with the telescopes. And this is targeting high school students. Particularly, we're targeting girls' high school students and Indigenous high school students. And this has been quite successful in encouraging girls into physics and then have them go into science at university. For example, in in some of the schools, they require girls to do physics in order to do the Telescopes in Schools program. And some of the girls have cited on surveys that they did physics because they wanted to do telescopes in schools. And then there's high success rate of these girls going into science at university. We're currently working on an Astro in the Classroom program, virtual program, and this was sort of triggered by all the shutdowns due to COVID. And we're due to launch it next year. So we used to send astronomers into classrooms. We're not allowed to do that at the moment. And so we're developing a program for primary schools where we're teaching the curriculum of astronomy, because in Australia, the curriculum includes astronomy now, but didn't in the past. And so the teachers are less comfortable in teaching the astronomy, but they have to. And so we have astronomers giving short presentations and then answering questions on their curriculum activities. And we're also, in conjunction with that, providing teacher training modules for astronomy. We're developing Indigenous Work Experience program, and we also have in production at the moment a virtual reality program for high school students. And this is specifically to teach parts of the curriculum to do with cosmology, the Epoch of Reionization, and hydrogen atoms and ionization. Now, finally, in the last part of my talk, I just want to quickly talk about Astro 3D gender initiatives. So we have quite ambitious initiatives in the centre. So our target is 50% women at all levels by end of 2021. We already have 50% women on the SOCs and invited and contributed speakers at all conferences and workshops. And we have significant funding for conferences and workshops. So we run our own, but we also provide sponsorship to other conferences and workshops, and we give them this requirement. And also 50% women nominations for awards and prizes. Now, it's not enough just to hire and recruit 50% women. We need to retain them. Retention is really important, which I'll show you in a minute. And so to retain the women and also to provide a supportive working environment for all centre members, we offer a range of different initiatives targeting retention, and that includes childcare at all events. We provide travel support for children and their carers, and this can be for men. All of these are for men and women, these childcare initiatives. We do diversity training for the whole centre, and that occurs every 2 or 3 years, so that we can make sure that all of our centre members are attending this training. We're offering mentoring circles. So mentoring programs are difficult to run where you have minorities, less people in minorities at the top levels than at the lower levels, because those people are become overcommitted. So we're running circles where we have one mentor and about 5 mentees, and this is run using a professional program. And this is working well for just improving people's outlook and achievement of their career goals. Now, I'm going to be talking about our women-only permanent positions and hiring, and also at women's advancement and leadership programs. We're offering those to ensure that women progress through their levels at the universities and reach their leadership goals. We also have leave for school holidays. All jobs are available part-time. People are making the most of that, so they are taking advantage of part-time positions, and in particular women are doing that, which is good. And we also conducting gender modelling, which I'll show you. So the approach to diversity is top-down. We started off with 30% women, and we're now over 40%, getting close to 44% at most of our levels. And it's top-down, which means that all of our high-level committees have at least 50 women. So, for example, this is our Executive Management Committee. This is the committee in charge of personnel management, hiring, retention, budget, strategic planning, programs. And as you can see, we have more than 50% women on this committee. Here's our team. So we've been building over time. This is due to the fact that there are more universities in Australia want to become members of the centre, and we've also been increasing in our numbers of students and postdocs, as well as the number of associate investigators and affiliates. So these are people who would like to become members of the centre and are going to help the centre achieve its science goals. So we increased from 140 to around, we've got around 240 now researchers, and then we have another 20 admin and management staff and education outreach staff. And so this plot on the right shows you the fraction of women at each level with time. And so what it's showing is how we started off in 2017 with around 35% women chief investigators and students. We had some, we've been in charge of the hiring of the postdocs, so we were already targeting 50% when we began hiring, and now we're very close to that. And two things we're not in control of are actually the students. Our government provides scholarships for students, and they're not selected necessarily by us. They're usually selected at college level. So across all sciences, those scholarships are allocated by the university. And if you get a scholarship, you get into the PhD program. If you don't get a scholarship, typically the students don't get into the PhD program. So it's very hard for us to increase our diversity in our student pool, but we are trying. This is a slow process because we have to actually increase the applicant pool, and this means improving the pipeline for women that is all the way from high school and undergraduate levels. Our partner investigators, these are people in our partner institutions overseas, and we're constrained by, and these have to be senior people, according to the Australian Research Council, who have established track records. So we're kind of limited to the fraction of women at the senior levels overseas here, but we are working to improve that now. Now, one thing we've been looking at is how the Centres of Excellence have been helping improve the culture for women across Australia in the different universities. And so Centres of Excellence in Astronomy have been running now for 10 years. And there has been dramatic changes, particularly introduced in the last 7 years. And a lot of these have been introduced by the Centres of Excellence and then taken up by the universities. And we also have now Pleiades Awards, which are run by the Astronomical Society of Australia. And those Pleiades Awards are like the Athena Swan program. They provide awards to institutions which are improving the environment and also the retention and promotion of women in academia. So now you can see, this is a survey I did last year, and you can see that almost all Australian astronomy institutions have these initiatives which help improve the climate for women. So they are running climate surveys every 1 or 2 years. They have a carers fund for travel and supporting children when they are going to conferences and workshops. They're monitoring their speaker diversity, but I think they should be actually having targets for that. Mentoring for promotion, that is now happening. Conference codes of conduct. So this is codes of conduct for your own staff for when they go away to conferences, because they're representing your organisation or institution. This is important to have. They're having family-friendly working hours. So that means no meetings outside the time, no meetings or seminars or colloquia outside the hours of 9:30 to 2:30, and this allows both men and women to drop off and pick up children from school. They're offering lactation rooms. This is a standard practice. And then having equity and diversity committees and policies. So all these changes are great. The question is, are they working? And so one of the things that I've been doing as part of our diversity initiatives is research into whether these initiatives are working. And so now we can look at the current fraction of men and women in Australian astronomy, and it's around 30% at the student level, and it goes up to 40% at level A. This is primarily, I think, due to the Centres of Excellence hiring initiatives. So we're targeting 50-50, and most of our hiring is at level A. These are the postdoc levels. At the higher levels, so the level B is similar to your assistant professor, and level C is your associate professor, and level D is like professor, and level E would be distinguished professor, and people don't necessarily reach that level in their career, some do. And so you can see that, and it's actually been like this quite constant with time. And the decadal plan target here is 33% women at all levels. And you can see Australia has not achieved that at those high levels. So I want to know why. So I made this pipeline stress plot, which this basically tells you the percentage change in cohort at the level transition. So the number of men and women who need to leave or are leaving the field at these transitions in order to fill the number of positions for men and women at the next level. And so it's the previous plot here is what we call the pipeline. This is a pipeline plot. This is a pipeline stress plot. So this tells you where the stress points are in the pipeline. And you can see that women here, many more women than men are leaving at level at the transition between level A and B, so between postdoc and assistant professor, and here again between associate professor and professor. This is actually really similar to what's happening in US astronomy, which is also showing a similar departure rate. So to produce these numbers, women must be leaving at 2 to 3 times the fraction of men. So the proportion of women relative to their cohort are leaving 2 to 3 times as much as the proportion of men leaving relative to their cohort. Okay, so now what I did is I developed full astronomy workforce models. So these are full models. They include, you can run them forwards in time. They have actual hires and promotions and people retiring and departures from a workforce. And so in these models, my workforce is all of Australian astronomy. And the reason I can do this is because I have access to all the data, and this is very fortunate and amazing. I mean, most countries don't have access to all this type of data. So I have the population data from the Australian Astronomy Decadal Plan Midterm Review. I have recruitment data available from the AAS Job Register and the Australian Research Council, so I know how many fellowships are offered and at what level, and how many postdocs are offered and at what level. I have retirement data from the Higher Education Research Database, which is publicly available. And I have promotions data available for all the universities, and that's in the Academy of Science Athena Swan application database, which is also available. So we can now see whether the decadal plan target is actually achievable. And so the top plot here shows the results of these models. I'm starting the models now using status quo of hires, departures, promotions, retirements. And then I just run them forward in time. We just see, is there enough women in the pipeline? Are there enough women in the pipeline? And are promotions happening quick enough to actually make any change? And the answer is no. No, we're not ever going to achieve 33% women if we don't make change. And so this is pretty depressing. Okay, what happens if we retain 50-50 women? So we saw that there's many more women leaving at specific critical points in their careers. If we try to retain them, can we achieve that at all levels? And the answer is no. And why is that? That's because promotions happen infrequently, not enough, and also that our hiring patterns are controlling whether or not we can achieve this target. If we did 50-50 hires, which quite a lot of universities are thinking about doing, some have already introduced it. So for example, ANU and the University of Sydney are now doing 50-50 hires. If we did 50-50 hires, we could achieve our decadal plan target by 2045. That's still quite far away, 25 years, but it means that we actually can achieve that. We never achieve 50% women with just 50-50 hires. Retention is also key then. We need both. Okay, so let's get more ambitious. What can we do? How do we fix this? Now, if we had 50-50 hires and retention, so let's just say we're just going to be fair, and we can hire from the international pool. We're not limited to the Australian pool for hiring. There's plenty of women in all fields of astronomy if we look at the international pool and not just the Australian pool. And we need to do a better job, much better job of retention. If we did that, then we could achieve our 33% women target much quicker. So we could achieve it by 2039, and we could achieve 50% women in 45 years. Now, some universities are going further. So the University of Sydney has affirmative action. In fact, our government has an Equal Opportunity Act, and in that act, it says, the Federal Government Act says that large organisations and universities must introduce affirmative action programs to correct historic bias in areas where there has been a historic bias. And so universities are picking up on this, and the University of Sydney has had 78% female appointments to these, to permanent higher level positions, C to E. And that has occurred over the last few years. So if I say all the universities adopt this, it's quite dramatic, and I don't expect all universities to adopt it, but let's just say they do. We'll achieve our decadal plan target in 10 years, and we'll achieve 50% women in 25 years. And so that's you know, that it just brings down the timescale. So this is work that really shows that what we're doing right now is not going to achieve those targets, and we actually do need to do something. And we need to either work on hiring and we basically need to work on hiring and retention in order to achieve these targets. Okay, so how do we achieve that target? We actually need to be doing retention, and that's difficult. We need to be running exit surveys. We need to know why women are leaving more than men. We need to change culture if that's what shows up on those surveys. We need to have recruitment targets. We need to do a better job of mentoring across the universities, and then we need to provide role models with good balance between work and family life. So studies have shown that just having role models is not enough, and women want role models with a good balance between work and family life in order to remain in the field. Okay, so that's the end of my talk, and thank you. I covered a lot of topics today in today's talk that we are doing in Astro 3D, so I'd like to invite you to ask any questions across the whole lot.
Thank you very much, Lisa. That was a fascinating talk. So I think we have time for some questions.
Charles, you should be able to unmute now.
Oh. Can you hear me?
Yes.
Oh, very good. Hi, Lisa. Thank you very much. So I wanted to ask you about the extremely low metallicity stars. How do you have a way of independently determining age and metallicity, or do you conclude, or whoever's doing this work conclude that these stars are the oldest stars because they have very low metallicity?
So the age is constrained with the GAIA data, and so they are modelled together, the age and the metallicity. We wouldn't be able to measure the metallicity without our AAT HERMES high resolution spectroscopy, but we wouldn't be able to measure the age without the GAIA data. And so you actually need both, and then they're both combined together in order to derive the metallicity. But the metallicity itself is done using the spectroscopy, so the full spectrum that we obtain. These are optical spectra, and so we're looking at it's iron and other species in the galaxies to determine how metal poor they are, and we're constrained by what lines are available as well in the spectrum. So some stars, it looks like they're poor in some elements and not others, and then other stars look like they're metal poor across the full range of elements. And this particular star was more enriched in other elements, but less enriched in iron.
Okay, thank you. And I wonder, while I've got your attention and the floor, the question of retention of in this case women as career progresses, is there a significant amount of anecdotal data of people saying explicitly why they made the career choices they made, and is it primarily work-life balance that's leading to the increased loss of women as they progress through the ranks?
Yeah, it has been done in physics, but not astronomy. They've done longitudinal surveys where they track women who are doing their PhDs, and at the beginning, they don't plan to leave. And then when they leave, they ask them why. And there's actually, there's 3 reasons primarily given in these physics studies. And then there was another reason that popped up in a separate astronomy study. So the 3 reasons that are given in the physics studies of why the women left after their PhDs are, one was a lack of role models with good balance between work and family life. One was a lack of good relationship with their supervisors, and that might be PhD or postdoc supervisors. And another one was, the other reason was that they didn't feel that they would be able to attain a senior position. And I think that's related to the role model thing as well, right? If you don't see many women at the higher levels, you don't think you're going to get there either. And then there was a study in astronomy which specifically looked at dual career couples, and the women were leaving more than the men to support the husband having to move to different locations. And so the conclusion for that was that that dual career couples and, you know, having to support the spouse's career choices was also a prime reason why women left the field of astronomy. So I would say that it's all 4 of those are probably the likely reasons that women are departing at a higher rate than men. And so means that we need to, you know, have a range of policies to address those. So dual hiring policies help. And then personalising science. This is something I didn't talk about, but we're doing this in the centre, is you have to show that the senior women, even if there are less of them, you have to show that they are having a work-life balance. So we have a newsletter that comes out every 2 weeks, and at the bottom we have a section called We Are People. We basically copied this from the Academy of Science, which is doing a similar thing. And it basically is just someone showing what they do in their spare time. And, you know, people are doing all sorts of things, right? They're doing sports and various hobbies and things. And it just, I think it just helps to show that, you know, we're not just the faces that we see at work. We're actually quite professional, I think, in our outside life as well. People are achieving really great things in other areas as well. So there's those things, but I think also the lack of relationships with good relationship with supervisor and postdoc advisors is very important as well. And I think there needs to be better advisor training in order to be able to build better relationships, and because I think we can't address 2 or 3 of those and not address the 4th and ensure retention.
Okay, thank you very much.
We have a question from Anna Rosen.
Hey, Lisa, nice talk. Actually, I just wanted to follow up with that. So you mentioned about, you know, with retaining women, that it's important to have more female role models at higher levels with a good work-life balance. But wouldn't it also be important too to also show that the men at higher levels can have a good work-life balance? And,
yeah, exactly. Yeah. So we do both. I mean, we don't just show women in our We Are People sections. We show men and women. And on our Slack channel, we have a work-life balance hobbies section where everybody can just post whatever they want. There's lots of people making very delicious food during the shutdowns. So yes, absolutely. I think you need to just show that people can have good work-life balance in astronomy. But I suppose in particular for younger women, they want to be able to see that your work life, if they want to have families, I think they need to be able to see that the senior women are able to have a good work-life balance that includes families and time with the children as well. And so I think that's simple. That's actually one of the reasons why I show my kids in my slide. You know, I did that where we're kids in a candy store, because it is important to show that we do have, you know, we have children, we're not hiding them.
Yeah, I guess one thing to just comment on too was, you know, I spent a few months at ANU a few years ago, and I remember my friends who were postdocs there but were from America talking about how the work-life balance that was presented at Mount Stromlo just kind of blew America out of the water. So
yeah, Mount Stromlo is a kind of special place. It is a really quite an amazing environment to work. It's actually a fairly quiet environment. You can get lots of work done, which is great, and also it's fairly, we call it laid back, fairly relaxed. Yeah, and so you can, it's totally fine if you've got sick kids to bring them into your office if you want to, or well, not at the moment actually, but we could before COVID. Now people wouldn't like that very much. And so, yeah, it is a relaxed environment, and I think it sort of always was quite relaxed like that. But you know, can be done in other places as well. And you know, we built our centre from ground up, and we're covering multiple universities, not just Mount Stromlo, and some of them are not like that. But within the centre, we do still have that climate at those universities, so you can, and it can have broader impact on those departments as well, which is what we're aiming for.
Yeah, and I guess my only point is, just to finish up quickly, was the way that the senior staff kind of showed that made it a lot more relaxed and comfortable for the postdocs and grad students to be able to include, you know, have a good work-life balance and not feel the pressure.
Yeah, I do think a lot of these things have to be top down. You've got to set a good example. Yeah.
Exactly. Thank you.